Hello engineers, this is one mechanical engineer, and in this video I will talk about ideal Brayton cycle. And in this video I will derive equation to find out the efficiency of open cycle gas turbine power plant. And if you are preparing for engineering service examination, then my video will be very helpful. So without wasting time, let's get started. First I will draw here open cycle gas turbine, so I can teach you everything what I actually want to do. I will first draw here compressor. There is one shaft between compressor and turbine, and this is commonly connected to electric generator. This is gas turbine. This is compressor. And here is process 1, here is process 2, this is combustion chamber, and fuel comes in the combustion chamber, and compressed air goes to fuel in combustion chamber. So air and fuel both get mixed up, and then gases come out. This is process 3, and this is process 4. So in the process 1, first atmospheric air enters in the compressor and it get compressed, and because of that when it get compressed, its volume get decreased and pressure get increased, and then it enters in the turbine in the combustion chamber. It enters in the combustion chamber, and here fuel is mixed in the combustion chamber and it get burnt, and after this gases goes to gas turbine and it rotates the gas turbine, and we can generate the electricity by using this. And it also used to rotate the compressor, and this is, and after it get used, all the air get expanded here, all the gases get expanded here. These gases goes to atmosphere again, and this process can be called as heat rejection process. So now I will draw here PV and TS diagram of this process. First I will draw here PV diagram. This is process 1, this is 2, this is 3, and this is 4. This is volume and this is pressure. Let's take a look here again, and this is process 1 and this is process 1. 2, 2, 3, 3, 4, 4, 4, 4. So first air enters in the compressor and it get out in the turbine in the combustion chamber. So when air get compressed, its volume, this is volume, this is temperature 1, sorry, this is P1, pressure at 1, and P1 is equal to P4, and P2 is equal to P3. I have to remember this. So pressure at the compressor and outlet gets same because in both these process it is atmospheric air. First atmospheric air enters in the compressor. So when it get compressed, its volume get decreased. So this is the volume 1 V1 and this is volume 2 which is volume 2. So volume is decreased here because when it get compressed volume get decreased, and in the process 2 pressure stays constant. So because of that P2 is equal to P3 because in the process 2 and 3, because during the process 2 to 3 pressure stay constant, and after that it goes to gas turbine and here it get expanded. So let me show here V3 and this is V4. So in the expansion process volume get increased. So here you can see volume is increased. V4 is more as compared to V3. So this is the PV diagram. Now I will show you TS diagram, which can be called a temperature entropy diagram. And before I show you the temperature entropy diagram, I will give you a name of these processes. So this is first process which is compression. So I will give here name isentropic compression. And this process can be considered as constant pressure heat addition, which is combustion chamber. And this is isentropic expansion, which happens in the turbine. And this is heat rejection, constant pressure heat rejection. So you might be wondering, these two processes are isentropic, compression and expansion. Both of these processes are isentropic. And you might be wondering what is isentropic actually. Isentropic means constant entropy, process in which entropy does not change. So that process can be called as isentropic. So I think you understand what is isentropic. Now I will tell you about temperature entropy diagram. This is temperature and this is entropy. During the process 2 to 3, which is combustion chamber, in this process pressure stay constant. So I will write here pressure stay constant. And during the process 4 to 1, which is heat rejection, when gases get out from the gas turbine, in that process pressure stay constant. So I will write here P is equal to C here. I will consider it as QS and I will consider it as QR. So S1 is equal to S2. So in the compression process entropy stay constant according to this TS diagram, but temperature get increased during this compression process. This is T3. And during the combustion process, this is combustion process 2 to 3. During the combustion process, temperature get increased and entropy also get, and this is the entropy which is S3. It also get increased during the expansion process, because when temperature increases, entropy mostly increases, and in the expansion process entropy stay constant, but temperature get decreased, but T4 is less than T1. Sorry, T4 is greater than T1. So temperature at the outlet of the gas turbine is more than the temperature at the atmospheric air. So this is everything I know about PV and TS diagram. So I think you understand this PV and TS diagram before I start deriving this expression. And before I derive this expression, I want to give the name of this process. Process 1-2 is isentropic compression. Process 2-3, which happens in the combustion chamber, and it is constant pressure heat addition in the combustion chamber. Process 3-4. Process 3-4, which happens in the gas turbine, and it is expansion process. So I will consider it as isentropic expansion. And process 4-1. This is process 4-1, and it is constant pressure heat rejection. And before I start learning this Brayton cycle, this ideal Brayton cycle, we have to assume lots of things. So there are some assumptions in this process. Assumptions number 1, which is compression and expansion is isentropic. You can see in the PV diagram and TS diagram. And second thing we have to assume is pressure losses in the system is neglected. And third thing we have to assume is heat losses in the system are neglected. And fourth one we have to assume is specific heat. It is known as Cp of working fluid is taken constant. And we have to take this working fluid 1 kg. So first I will take a look at heat addition, constant pressure heat addition, and constant pressure heat rejection, which is process 2 to 3 and 1 to 4. Both these processes are constant pressure. I will turn the page. And before I start explaining all of these things, I want to tell you the expression, I mean formula to find out the efficiency. So formula to find out the efficiency of the gas turbine is net work done upon heat supplied. And net work done is heat added minus heat rejected. So first I will find out what is heat added. Heat added is, if we take a look at this process, heat added during the combustion chamber, which is 2 to 3. So I will write here MCP, and during this process, during the combustion process, T2 and T3, T3 is more than T2, so I will write here T3 minus T2. This is something when heat added, and now I will write here heat rejected. After X work done, this is something which happens after expansion process. So when heat get rejected, when these gases get expanded in the gas turbine, then it goes to the atmosphere and here rejects the heat. So this is, if we take a look at TS diagram, then it is 4 to 1. So T4 is more than T1. So I can write here MCP T4 minus T1, and we have taken here M is equal to 1 kg air. So we can also write here CP T3 minus T2, CP T4 minus T1. Now I will put both of these values in this net work done, and if I will put this here, then it will be, so first is heat added. So heat added is Cp T3 minus T1 or T2. minus heat rejected is Cp T4 minus T1, and heat supplied is T3 minus T2, and I can write this equation as and I can cancel this, I can cancel this, and I can cancel this. So this equation will become this is the formula to find efficiency, but I can find the value of T3 and T2 if I want. So I will do that first. And if I want to find the value of T3, I mean if I want to find the value of T2, then first I will consider consider process 1 to 2, which is process 1 to 2, which is compression process. I will turn the page. And T2 is more than T1 and P2 is more than P1, and gamma minus 1 upon gamma, this is the formula, and this is the pressure ratio, and we can take it as Rp. So this formula will become like this, and then I will consider the process. I want to find out T3, so I will consider process 3 to 4, which is 3 to 4 is expansion process, 3 to 4 isentropic expansion process. T3 upon T4 and P2 upon P1, gamma minus 1 upon gamma. And sorry, I have done some mistake. P3 upon P4 T3 upon T4 is equal to P3 upon P4 raised to gamma minus 1 upon gamma. But if you will take a look at PVTS diagram, then you will find here that P2 is equal to P3, so I can write here P2 instead of P3, and P4 is equal to P1, so I can write P1 instead of P4. So I will write here P2 instead of P3 and P1 instead of P4. So it can be written as Rp gamma minus 1 upon gamma, because P2 upon P1 is equal to Rp, and I can write this equation as, and I can also write this equation as so now I will put the equation, put the value of T3 and T2 in this equation. I will put here T3, value of T3 and value of T2. I will write this formula again. So value of T3 is and value of T2 is T1 Rp gamma minus 1. I can take Rp gamma minus 1 upon gamma as a common. And this equation will become T4 minus T1. I can cancel both of these, so this equation will become this is the final equation to find the efficiency of open cycle gas turbine, and this is the pressure ratio. And if I want to increase the efficiency of gas turbine, then I have to increase the pressure ratio, and which is P2 upon P1. When it will increase that, then efficiency will also increase that, and if it will decrease, then it will also decrease. So this is it for today. God bless you.